Hi, my name is Alex Newell, and today I'm going to be teaching you about semiconductors and why they're so important. So, I am a second year PhD student in the Electrical and Computer Engineering department at UNM with a focus in optoelectronics. Currently, I work at the Center for High Technology Materials, which is a lab at UNM, and I specifically fabricate these devices using a molecular beam epitaxy reactor. And I know that's kind of a mouthful, but I'll break it down later, and it's actually not nearly as complicated as it sounds. So, first, I'd like to start off with what a semiconductor actually is. So you can kind of classify materials based on their electrical resistance. A conductor conducts electricity very easily, so that means it has very low resistivity. This includes things like gold and copper. Insulator, on the other hand, conducts electricity very poorly, and so therefore it has a very high resistivity. This is things like rubbers and plastic, and semiconductors are kind of right here in the middle. So what actually makes a semiconductor a semiconductor? Well, a conductor conducts electricity so easily because it takes virtually no energy to push electrons out of the valence band into the conduction band. And I'm probably thinking, whoa, like, what is a band? Well, a band can be thought of as an energy level that the electron is in. So the valence band is the energy level that the valence electrons are in. They all share the same value of energy. The conduction band is when these things get knocked out of the valence shell and they become basically free electrons able to conduct, hence conduction band. So it's important to note that for the valence band, the electrons are bound to the atom, and for the conduction band, the electrons are not bound to the atom. So going back to this slide, insulators, as opposed to conductors, are on the other end of the spectrum, and so they have a very wide band gap. This means that there's a very large difference in energy from the conduction band to the valence band, which means that it requires a lot of energy to push these electrons out of the valence shell and into the conduction band where they can conduct electricity. Semiconductors are very interesting because they have a narrow band gap, and we're kind of able to manipulate the band gap here and there, a small value, which wouldn't really do anything for a wide band gap material. It would still be a wide band gap. But in a semiconductor, these small manipulations we really have a lot of control on whether they conduct or they don't conduct. So, why do we care? One implication is the modern computer. A long time ago, when we started making computers, we would have to store units of information called bits in these vacuum tubes. And I'm not exactly sure how they work or anything, so don't ask. But the key takeaway is that they're bulky, and one computer was basically the size of an entire room. In 1943, Thomas Watson, who was the president of IBM at the time, predicted that there would be a world market for maybe 5 computers. And as we know today, this is wildly inaccurate. And so it's kind of widely regarded as the worst tech prediction in history. So he was so wrong because he didn't foresee the miniaturization of these devices, of these kind of things that are able to store information. If we're able to control whether a semiconductor conducts or doesn't conduct, that means it can store a little bit of information. So therefore, instead of the giant room full of vacuum tubes and electrical wires and stuff like that, we can fabricate a computer that's smaller than the size of your fingertip, which is pretty crazy. Another application of semiconductors are optoelectronics. An optoelectronic device is a device that's capable of converting light into electricity or electricity into light. Earlier, when I was talking about the band gaps, you might refer to the conservation of energy and ask, well, where does this difference in energy actually go? Or where does the energy come from? Well, a photon, actually. So when an electron, this is the electron, jumps from the conduction band into the valence band, it's going to emit a photon with the same energy difference. The photon energy is given by this equation, E equals Planck's constant times its frequency, hv. On the contrary, if an electron is in the valence band, it's going to require a photon of the exact amount of energy to jump to the conduction band. So this is how electrons and their transitions, we call them optical transitions, create light. So how do we use this information? Well, let's do a little exercise. We're going to design a solar cell. So knowing that E equals hv, and here I've provided the spectrum of solar radiation, which is basically irradiance, versus wavelength. Irradiance is probably an unfamiliar term, but it's basically light intensity. So that means out of some unit area of sunlight that gets hit, the most photons are going to have a 500 nanometer wavelength, as you can see by this peak. So in order to get the most out of our sunlight, let's go ahead and use something that can absorb this 500 nanometer wavelength. But how do we do that? Well, E equals hv. So the frequency can be calculated by the speed at which the particle is moving. For us, that's the speed of light, denoted as c, divided by the wavelength, which is 500 nanometers. So the speed of light is 3 times 10 to the 8th meters per second, and the wavelength is 500 times 10 to the negative 9 meters. So that equates to 6 times 10 to the 14 hertz. Planck's constant, as he calculated, was 4.14 times 10 to the negative 15 eV seconds. EV stands for electron volts and is just basically a unit of energy. So multiplying these things together, we get that the E of that light is going to be 2.47 EV. So now what? Well, we need some kind of material with a band gap around 2.47 EV to absorb that 500 nanometer wavelength of light. So this is where we have one area of control for our device, and it's that material choice. So this is a chart denoting band gap versus lattice constant. I'm not going to get into lattice constant for this lecture, so let's just pay attention to band gap. Germanium has a band gap of roughly, I don't know, what is that, 0.75 or something? I'm actually not quite sure why 0 is here, and interesting. But as you can see, aluminum phosphide is probably our best candidate to absorb that 500 nanometer wavelength of light, as its band gap is roughly 2.5 EV. So let's take a chunk of aluminum phosphide, let's put it out into the sunlight, and let's see what happens. So in comes our 500 nanometer wavelength of light, and it's going to hit an electron in the valence shell. That electron is going to jump up into the conduction band, which is then going to leave a vacancy in the valence band. We call these things holes, and we actually treat them like particles. Even though they're just the absence of an electron, it's actually a lot simpler to treat them as positively charged particles in the electron's absence. So the electron jumps into the conduction band, leaving a hole in the valence band, and then what? Well, within milliseconds, the electron's just going to fall back into that unoccupied space that it left, and it's going to then emit a photon with 500 nanometer wavelength. So all we've basically done is just reflect this light with maybe an extra step in between. So that's not good. How do we get the electron to do stuff for us? So what we want to happen basically is for the electron to move one way and the hole that it left to move another way, so that the electron doesn't just fall into the hole, recombine as we call it, and emit the photon. But what's going to do this? An electric field. An electric field points from a positive charge to a negative charge and basically influences a charged particle. So if we have an electron in a hole here, and we put a positive charge on the right side and a negative charge on the left side, then it's going to set up an electric field, this charge separation. And that electric field is going to push the electron over to the right towards the positive charge, and the positively charged hole over to the left towards the negative charge. So great. That's exactly what we want to happen. But, how do we get an electric field in a material? Well, that has to do with something called doping. Doping is when we intentionally add impurities into the semiconductor in order to change its properties. So, for example, here we have a crystal or a lattice of silicon, just a different array. And what we do is we intentionally add a phosphorus atom into this array. The phosphorus atom, if you look on the periodic table, has 5 valence electrons. All of these silicon atoms only have 4 valence electrons. So each of these 4 valence electrons in silicon's shell are going to bond with the adjacent silicon atoms. For the phosphorus with 5 valence electrons, 4 of them are going to help bond with the silicon atoms, but this last one here is just kind of the odd one out. So it turns out that this electron is very loosely bound to this phosphorus atom, and so it's free to jump into the conduction band, basically. It's also important to note that when this electron leaves from this site, then it's going to leave the phosphorus positively charged. The phosphorus atom becomes an ion because it's neutral when it has 5 electrons, 5 negative charges surrounding it, but it's going to be positive when it only has 4 electrons surrounding it. So this is one type of doping called N-doping, and phosphorus can be called a donor impurity. Donor impurities, you can think of them as atoms with one too many electrons, which then allows it to donate 1 electron. Acceptor impurities, on the other hand, are atoms with one too few electrons. For example, 3 valence electrons. So that allows it to accept electrons. And you can think about it as having a bunch of free holes moving around. So if we have an N-dope region and a P-dope region, what happens when we put them together? This is called a p-n junction, and it's very important. And what happens basically is when you put them together, the free electrons, which are just moving around randomly, are going to be able to move into the p-dope region just because of diffusion. The holes, the free holes on the p side, are moving all around, and so they're free to diffuse into the n side. And remember, when this electron, this free electron, moves over to the p side, it's going to leave that positive ion, phosphorus for example, still over on the n side. So when a bunch of positively charged holes come over, and in addition with the positively charged ions that are already in the n side, it's going to create a net overall charge, positive on the n side and negative on the p side. This charge separation creates an electric field. So hooray, we have our internal electric field that is then therefore capable of influencing the holes and electrons. So let's see what happens when we put this p-n junction in sunlight. So we wait around, and in almost no time a photon with 500 nanometers comes, which then creates an electron hole pair by exciting the electron out of the valence shell into the conduction band, leaving the hole. And this charge separation, which then created the electric field, is going to attract the electron over to the left side. Oops, messed up the order of that one. The hole over to the right side, and the electron over to the left side. So that means they're not going to combine again and create another photon. So that's great. But we still have one more thing to do. As more and more light comes, it's going to create more electron hole pairs. The electrons are going to move over this way because of the electric field, and the holes are going to move over this way because of the electric field. But as more and more electrons come over here, which are negatively charged, they're going to influence the overall positive charge on this side and effectively cancel it out after a while. So we need some kind of sink, I guess, to basically extract these electrons in holes so they don't just accumulate over here, reducing the electric field. So all we do is we just attach a contact to each side and then put a wire. Let's connect this wire to a battery, say. So that means that the electron is free to move through the wire, and it's going to help charge the battery, and the hole is going to do the same thing. Therefore, we don't get an accumulation of electrons over here and holes over here. So the electric field gets maintained, and so that more sunlight can have the same effect. And so that's how we get current out of a solar cell. So great. Now this is all fine and dandy on paper and whatnot, but how do we turn theory into practice? Well, that's where molecular beam epitaxy comes in. So this is a photo from CHTM, the Center for High Technology Materials, and this is what we call the right-hand side and left-hand side reactor. I know it looks really complicated, but basically all it is a big vacuum chamber and some fusion cells. I'll show you a diagram later. But you might be thinking at this point, well, so how does this tie into globalism? Well, this read system that we use to monitor growth of our semiconductors is made from Germany, or made in Germany. The gallium telluride source is from Japan. We buy these valve shutters from Switzerland. The Pfeiffer turbo pumps, Pfeiffer is a German company, and even the whole MBE shell was made in Great Britain. So, as you can see, this science is rooted in international collaboration, which can be hindered or helped by international relations. And for the sake of science, and everything, let's hope it's always helped. So, good international relations help science and everybody. So, even though it looks all complicated, it's really simple. All it is this big vacuum chamber. We use our handy Pfeiffer pumps to get rid of all the air and stuff. And then we have these pure elements that we hold in these fusion cells. Wrapped around these cells are little heater wires, which heat the different sources up to various temperatures. And basically, we want them to vaporize. And so once they vaporize, there's a bunch of vapor molecules in here. And if we open the shutter of one of these devices, then the vapor is free to run out. And because they're all pointed at the substrate, which is what we grow the device on, then the flux of particles comes through here and condenses onto the substrate, where it then crystallizes and we can get our semiconductor. So, great. So, the structure for our solar cell is going to be a p-type aluminum phosphide that is going to be doped with beryllium. Beryllium is an acceptor impurity because it has 3 valence electrons, so it accepts electrons. Our N region is going to be doped with tellurium because tellurium has 5 valence electrons, which means it donates electrons, so that we can make our internal electric field, and so that holes and electrons will be separated once they get created. And our substrate is going to be aluminum phosphide. So for the growth, I'm going to go ahead and put the substrate into the growth chamber right here. I'm going to pump out all the air. We want to pump out all the air so that things like oxygen and nitrogen don't get incorporated into our semiconductor. When different elements, impurities get added there, then it can lead to a lot of different defects and stuff, which hinders the capabilities of the device. So I'm going to heat up my fusion cells. This one's aluminum, phosphorus, beryllium, tellurium. I'm going to heat them up, and then I'm going to open the aluminum, phosphorus, and tellurium shutters. And then I'm just going to let that go for a while, and after some time, I've grown my N-type aluminum phosphide layer. Then I'm going to go ahead and close this tellurium shutter and open up the beryllium shutter. Once that's open, the flux comes out of the beryllium instead of the tellurium, and I'm going to get my p-type layer. And then I'm going to close them all up and take out the substrate. So the next thing we have to do is just basically attach a wire to it. So to summarize, all that we've considered in creating this device is basically such. So we chose aluminum phosphide because its band gap matches the energy that the maximum intensity wavelength of sunlight has, which is about 2.5 eV. Then we used appropriate doping so that we set up an electric field which is used to transfer carriers and induce current. Don't pay mind to this upside down E, I just could not figure that out. So, um, so a solar cell was one example of an optoelectronic device where it turned photons into electricity, basically. But other optoelectronic devices include photodetectors, light emitting diodes, and lasers. Photodetectors have a pretty big influence in military devices. For example, right now my group is being funded by the military to create a infrared detector, and that's really important for things like military because thermal bodies emit light at the infrared frequency. So if we have a good infrared photodetector, then we'll be able to see people in the dark, which is obviously advantageous. So another big use is directed energy. Directed energy really found a foothold in our military in roughly 2014, and it really took off because of its advantages against other weapon systems. The best example I have of this is anti-missiles. So our current strategy to block a missile coming in towards the United States is to shoot it with another missile. And while we do have missiles that can do this, it costs about like a couple $1 million each missile. You know, these things are not cheap. But the defense contractor, Lockheed Martin, just has recently displayed their new high-powered laser, which is basically able to just point it at an incoming missile and blow it up. So instead of spending millions of dollars on these fancy missiles, all we have to do is spend money on the energy it takes for a laser to blow it up. So that's great. And while we don't make any lasers that can blow up missiles in CHTM, it is very important for laser research to be carried out. So the military and Air Force do submit a lot of funding for these type of projects to be examined. And so, yeah. So, in conclusion, semiconductors have completely reshaped society, and it's pretty wild that so few people even know what they are. So I hope I gave you some insight into the most important development in the modern era and how globalism has influenced it. So thanks. Take care.